Hello everybody, as we know that we are in the third part of the course which is on testing, and within this third part on testing now we are in the advances of embedded system hardware testing, in which case we have already discussed about two main aspects. One is about some kind of very realistic fault models which are required for advanced embedded system hardware, like real time fault models, or we can say delay fault models which meet the real time requirements. Then we have seen that basically what is called built-in self test, that as these fabrication technology of the embedded hardware are becoming more and more sophisticated, so we have to test each of the devices before they start up, and we have discussed at length in the previous lecture on built-in self test. Now in the next two lectures we are going to see a very important concept, a very new concept of testing, which is called online testing or concurrent testing. That is very important. So that is basically, see, all these first two test cases, that is lecture 1 and I am sorry, this is lecture 2, basically, or all the basic concepts of test we have seen till now are something called an offline testing. So what do you mean by an offline testing? So basically what do you mean by an offline testing and BIST? We can categorize both of them in this part of offline test, because offline test is something like when the device is not doing its regular activities. So the first basic concept of test, which we call it manufacturing test, or we also call it as ATE based testing. So in ATE based testing, what happens? Test patterns are generated beforehand by ATPG algorithms, and then the device is placed into the automatic test equipments. Patterns are applied to the circuit under test, that is the device, and the expected fault free response are analyzed by the ATE. So basically it requires something called a non-operational mode of circuit, and of course it is not at all deployed in the system at all. So basically already discussed so many times that ATE based testing means the device is fabricated, pushed in the tester, and you test by physical signals. So of course there is no question of operational mode of the circuit, because the circuit is not yet deployed in the system. So the main issue here is that you can test it only once after its manufacturing. So if it develops any faults during its lifetime, this test technology cannot cater to that. So for that we have seen something which is called built-in self-test. So difficulty of ATE based testing is basically at speed testing is bit difficult, or with expensive I should say, because more number of test patterns means more high speed ATEs are required. And also secondly, basically we should also add that it is an offline test. Offline test basically in the sense that if the system develops a fault after it is deployed in the system, ATE based testing cannot handle that. Secondly, to do this, what we have seen, to address such cases, we have seen there is something called a built-in self-test. So built-in self-test, basically the test pattern generator and the test response analyzer are on-chip circuitry, and what it allows, it permits to test the circuit under test every time when it is powered on. That is, first is called offline, or simply I should call it ATE based offline. After manufacture, the chip is tested, sold to you. Then after that, if some defects come up after it is deployed in your system, you have to use something called built-in self-test. But again, always in both the cases, like ATE based testing or built-in self-test based testing, we call it as an offline test, because we need to withdraw the circuit from normal operation for testing, which always may not be permissible. So I mean, I am not going to the second clause right now, but this DFT based test, this ATE based testing or BIST based testing, what you have to do in ATE based testing, forget about the normal operation of the circuit, because the circuit is not deployed yet. But even in case of BIST, what happens, you have to halt the normal operation of the circuit, because already we have seen the architecture yesterday, that is a multiplexer. So either you give the test patterns from the hardware pattern generator, or the normal inputs come through. So in that way you have to stop the operation of the circuit, and then you apply some patterns, or in fact you should not call it stop, basically even before the circuit starts its operation you have to apply the BIST. So while the BIST is going on, normal inputs cannot come. So at many points of time, sometimes not only BIST is applied at the startup, in many cases nowadays people apply BIST in intermediate points of time also. That is, if you have some ideal time of your circuit, you can apply the BIST and test it. But in all these cases you have to be very important to remember that normal circuit inputs cannot go. So the circuit has to withdraw itself from the normal functional mode, or if it applies at the start time, so of course the circuit has not started its operation yet. So all these test technologies which we have discussed at length in the last 2-3 weeks are basically all offline. Why offline? Because the circuit is not doing its normal operation, or basically or it is not yet deployed even. Even if you are talking about BIST, still the circuit has to stop its work, or it is applied at the startup, so that the circuit cannot, or in all these procedures, the circuit cannot be tested while it is doing its operation. So either at manufacturing, after manufacturing, or just before it starts its job. Now a very important question comes. See, I have a very important mission critical application like a anti-locking brake system, or it is used in automatic avionics control. So this system is doing its operation, and meantime a fault develops. What you will do? So the direct answer should be, I should stop its operation immediately, and as soon as possible I should switch to a redundant module. So that's okay, that is the only way you do, that is actually fault tolerance. But there is someone to detect that the fault has occurred online, and in that case you cannot stop the circuit from doing its work to test it. In other words, I cannot say that, hey, I want to test this circuit, so stop its operation, I want to test it, if only fine, then you can start its operation again. That is not possible in mission critical, in any of the systems basically, because if you want to stop somebody's job, then basically either it will be delayed, you will lead to deadline misses, and so many other things can happen in picture. So in most of the real-time systems or real-time embedded systems, there is no liberty to stop the operation of a circuit and test it on the run, and then again say that, hey, this is fine, you can start the operation again. So that actually philosophy will not hold in any of the real-time embedded systems, because we are very hard pressed on timing requirements. So therefore, another class of testing, which has a very new concept of test has come up, which is called online testing, OLT, or also called concurrent testing. It can be defined as a technique to monitor a circuit and detect the occurrence of a fault within a finite time of its occurrence during its normal operation. Very important to observe the clauses. It is called monitoring. Circuit is doing its job, you are monitoring what is happening, because in all offline testing you stop the circuit and you can apply test patterns at your will. Because ATPG means, as you have seen, you are going to generate very good test patterns, that these 5 test patterns are very good, they can detect all the faults and their minimal set of test patterns. So you can apply that, but for that you have to stop the operation of the circuit and apply your desired patterns. But when the circuit is doing its normal job, then basically what? Then you cannot apply your required patterns. Patterns are already coming, which is its normal flow of operation. You can just observe or monitor the circuit's operation for those patterns, and if any fault is detected, you have to do some action. So therefore, there is no test pattern generator to generate test patterns in online test. Online test, basically you cannot stop the circuit from its operation, so there is no test pattern generation required, because you cannot apply any test patterns at your will. Normal inputs are coming, and you have to observe whether there is some deviation from the normal behavior or some fault is detected, and then you have to decide the occurrence of a fault within a certain finite delay. Why I should say finite delay? Because a fault has occurred and you are not able to detect it for years, will actually lead to catastrophic situations. Because in case of online test, you do not have you cannot apply your desired test pattern so that you can immediately detect the fault. That you cannot do. You have to only rely on whatever patterns are coming or input patterns are coming, and you have to observe the circuit based on some kind of techniques as we will discuss today, and then you have to declare whether the circuit is having any faults or not. And that also our technique should be such that after the occurrence of the fault, you should do it within a very short amount of delay. So they are saying there is no test pattern to generate test set, because you cannot apply any test set, but of course there are a lot of DFT circuitaries which will basically use these patterns that are normally coming to the circuit and use it to find out whether there is any problem in the circuit or not. So the philosophy I can tell in a very nice nutshell, that in test mode you can apply your patterns and get the circuit tested, but in online testing you do not have any patterns, because you cannot apply any patterns. So whatever normal patterns are coming in its normal course of operation, you have to use it and you have to monitor. Basically you have to monitor the circuit and find out whether any problem is there or not, and that has to be done without stopping the circuit. So if you cannot stop the circuit, means you have to totally rely on whatever inputs are coming in normal course, and based on that you have to detect whether a fault is happening or not. So it's a very difficult way to do it, and very expensive also, because you have to put lot of extra circuitries to do all this. Because in case of offline test, we have seen the extra circuitry in sequential circuits are nothing but your scan chain, and you have to find out basically your patterns and you can analyze them. But in case of online testing, things are becoming extremely difficult. With this, I can just take you 2 minutes for a very interesting technical story on this. I think we all know about our very famous cardiac surgeon Debi Sethi. So once he went with a car to a person for repairing. Then the car mechanic said that we also repair the car heart, you also repair human heart, but your and our pay difference are so high. So why is it? The answer was very interesting, that you do a offline repair on the car and I do a online repair on the human heart. That is, you stop the car's operation, you remove the engines and repair it. But I cannot do that on a human being. Human heart is running and I have to do the repair or test on that. So that is the philosophy of online and offline test. Offline test is a pretty simple job. You stop it and test it. But online testing means the circuit has to do its normal job. In that period of time, you have to do it. And nowadays, it's a very, very important concept coming in all embedded systems, because all mission critical systems are having basically embedded electronics. Car avionics, car cruise, ABS automatic braking system, even the whole aircraft control is based on embedded controllers. So it's a very, very important stuff which is coming into embedded system testing. So we have dedicated 2 lectures on that. So today we will see some of the techniques, and in next class some other kind of techniques for online testing, or sometimes also called concurrent testing of hardware in embedded systems. Basically, if you look at the online testing of VLSI or embedded systems can be mainly categorized into signature monitoring in finite state machine, self-checking design, partial replication and online based. So today basically we will try to have a look at the first 2, because the other 2 will be looking at the next class. They are slightly simpler in theory sense compared to the first 2. So what do you mean by for signature monitoring based techniques for online testing? So whenever we call online testing in terms of finite state machine modeling, so we all know that all sequential circuits can be modeled in terms of finite state machine. Then we find out some kind of signatures in the finite state machine model of the circuit. And then basically the signature is such that the runtime signature of a faulty circuit is different from the normal circuit. And of course, you cannot, if you just arbitrarily take any input patterns or any input sequence or any state encoding sequence, that will not be a signature. So signature has to be very well quantifiedly found out from the FSM model. That is, circuit is there, you make an FSM model, and therefore then very carefully select some state bits or output bits, so that the normal flow of the circuit and the faulty flow of the circuit, the signature will be different. Now of course, if I take all the output bits and all the state bits, then of course if there is any deviation from the normal behavior, you can catch it. But in that case, your monitor itself will be the circuit again. I will give you an example and I will tell you that again one thing you have to know, that whatever extra circuits you are using for monitoring should not be as large as the circuit itself, because then nobody will take your technique. That one circuit is given to you and the circuit you are applying to monitor it, which is as large as itself, because then who is going to have a fault probability? Your circuit under test or your working circuit may have a fault, and if you have a very large circuit also to monitor it, that may also have a fault. So nobody can keep a faulty or a similar kind of a fault nature circuit for its monitoring. Something like this, a circuit AX is there which is doing your job. You are putting another similar circuit to monitor it. Both have equal probability of having failures online. So you will not rely. So basically what happens, so in this case what we do, we take a circuit under test, which is your working circuit, it will be quite large, and then you take a miniature version or you take a miniature modeling or miniature sized online tester to monitor it. And it is expected that, and statistically also we have found, if a circuit is more the larger a circuit is, more number of gates and more number of faults it will have. So higher probability of faults or higher probability of development of faults in a bigger circuit is there compared to a smaller circuit. So our philosophy is that for online monitoring, the circuit under test should be large and the monitoring circuit should be small. So therefore, we cannot explicitly have such kind of signatures so that the monitor itself becomes as large as the circuit. So we have to take certain bits of the circuit state encoding, certain bits of the output, so that you can make a signature, so that if the normal circuit is there and the faulty circuit is there, the signature will be different in the faulty circuit. But again, this monitor size should be small, and there is something called a signature invariant property, that is the bits will be used to make a signature should be such that the normal and the faulty behavior should be different. But always it may not be possible, just like we have seen in the last class or in the few classes already we have seen that there is something called signature compaction. In BIST you have seen that there is something called output compaction. We do output compaction to reduce the ROM. So sometimes there may be aliasing. So similarly in this case, if you are making a signature that is nothing but lossy compaction, so sometimes some faults may be aliased. But still there are a lot of techniques to improve such signature invariant properties, so that even there should not be very less or no aliasing. But anyway, those details coding theory will not be going into. Rather, this course we are going to give you a broad idea that what is the signature monitoring based techniques, and you can easily appreciate that there will be aliasing. So for example, this is some circuit, and this is the finite state model. So you can see the state bit represents 000, 001 and 101. And if there is a fault, there is a back loop. there is a self loop which is in the fault, and it is in normal case there is no fault. So this is. Now you can tell me that if I want to make a monitor, basically what you can do is that if you say that I can just observe that there is a basically it should go like this and there should not be any kind of a loop like this, I want to make a circuit to monitor it. So in fact you will be landing up in modeling a circuit like this. What I mean to say is that if you want to observe that there should not be any kind of a loop in this position, and if the loop comes I will declare is an error. So I want to make a monitor like this. That means basically you are making a circuit like this to monitor this. So that is an explicit monitoring of this circuit, which that we do not like because of the area overhead. Rather we would like to take a signature. So if you assume that this is the only fault that can happen, or the fault effect basically. So what we can do, we can make a signature which will be comprising of this bit or the last bit of the circuit. So what is the signature pattern? If you see 0, then 1, then again 0, then again come back 1, and again it's a 0. So it's alternating zeros and ones. 0, 1, 0, 1, 0, 1, that fold. So this is a normal, this is a signature under normal case. But in this case what happens, if there is a loop over here, so signature will be 0, 1, 0, and there will be a repeat 0. So if the repeat 0, you know that is a. So that now you can easily observe that to monitor this circuit, the circuit size will be much lesser than the circuit corresponding to this finite state machine. But of course, as I told you, there can be lot of aliases. In this example, there may not be any aliasing because, but I think from the, because this is a lossy compaction based scheme. So from the BIST examples I have given you can easily appreciate that there can be some kind of aliases. And there are a lot of other techniques to remove this fault aliasing. Sometimes they modify the circuit itself so that the invariant property is preserved. So what is the invariant property? Invariant property is that whatever signature you select, like for this case signature, our case is the last bit of the circuit, LSB of the finite state machine states. So the signature invariant property is that with this failure or whatever the failures or circuit faults you have considered, the normal signature will always be different from the fault signature. So always it may not be possible, as I told you, for a given signature in a given circuit. So there are a lot of techniques, means which is you can read through, which are called means techniques for, which are actually basic idea is called to maintain the signature invariant property or maintaining signature invariance. There are a lot of techniques to do that. Sometimes we change the signature, sometimes we modify the circuit itself, so that these invariant properties always get maintained, and there are some other techniques to do that. But in this course or in this slide I have tried to give you an idea what is a signature and what is signature invariance, and how to maintain signature invariance is a long story which I am not going into. But of course you should appreciate that without such ensuring such signature invariant properties, not all faults will be detectable. There can be aliasing. But why do you take a signature? To reduce the size of the monitor circuit. So in this case I have shown you that you have to, this is a signature of alternating zeros and ones, this is a signature, any error you will get double zeros. This is only assuming that there is only one fault of this nature in the circuit. So whatever I told you, to obtain a signature with signature invariant property, the state assignment procedure have to be modified to take into constraints related to such an invariance. There is a lot of theory in picture. So in which case if we say that the alternating zeros and ones is my signature, and that should be the invariant one. So there are a lot of techniques like state bit encoding, state bit modification, and there are several other ways which will require to change the circuit structure or redesign the circuit structure so that such invariance is required. And many people may not like this because you can do lot of things with the DFT, because the monitor is the test designer's prerogative. But I am the circuit designer and this is my finite state machine design. Without changing the basic functionality, if I do certain kind of modifications, I may be very unhappy about it. Well, of course, you cannot change any functionality of the circuit. Like for example, I will give you, this is a 3-input AND gate. Whatever job you do with this is also the same job will be done by this structure also. But we may say that there can be a delay there may be slight delay increase because of the two levels of the circuit. So in that way, people sometimes modify the circuit design or state encoding so that the invariance is maintained. And with the invariance maintained, there will be no fault aliasing. But we call it actually intrusive nature of a circuit, that is you change the circuit itself for online testability. So sometimes people do not appreciate much about the circuit invariance or circuit intrusiveness. So that is one challenge in finite state machine based online testing, that it changes the circuit at many points of time. Finally, also the second problem is that finite state machine is not a scalable model. So for very large circuits you cannot at all make a finite state machine itself. So no question of how do you test it using this signature monitoring property of FSMs. So it was a very good starting point for online testing circuits. For this was one of the first proposed methodology which which have done online testing for small circuit, but when things started becoming larger, this technique could not be applied, mainly for scalability issues, and also even in the beginning phase also some people were not happy with it because they were asking you to change the circuit structure to maintain signature invariance. Then there is some another concept came up which is called self-checking design. A self-checking circuit can be defined as the ability to verify automatically if there is any fault in the circuit without the need for externally applied test patterns. So obviously here also in the same case there is no externally applied test patterns, only you have to look at the monitors. But they have given a very specific name for such class of circuits, in which case without applying any external test patterns you can obtain the circuit, you can decide whether there is a fault in the circuit, and they encode the circuit outputs using some coding theory. Some codes like parity codes, Berger codes, M out of N codes. Even you can tell me that signature monitoring is also some kind of a self-checking design, because there is a signature invariance. You have to check just the signature invariance property. But self-checking design was a new term which was coined after this finite state machine signature monitoring, in which case they say that a circuit is self-checking if you are able to automatically determine whether there is any fault in the circuit without any applied pattern. In how all the outputs of the circuits will be always encoded by a particular mechanism. It will be either parity, I think we all know about parity codes, that is the output if normal will follow a odd parity or even parity. Sometimes there is a hot one encoding, so the output of the circuit will always be hot one encoded, or M out of N, like if there is an N bit output, always M number of ones will be there for all cases. So that way the output of the circuit will be always encoded by a particular encoding, encoded theory, by coding theory encoding, and any violation, any fault in the circuit will lead to a non-code word. So that is the basic idea of a self-checking design. So I will take an example, so it basically looks like that. So the functional circuit, inputs are normal flowing inputs, whatever is coming you have no control on that, but the outputs will always be a code word. Either it's a parity code, M out of N code, Berger codes, many coding techniques are there and they will be there. And there is a checker, the checker will just check whether the output is a proper code word or not. Even parity, odd parity, M out of N, hot one. So if the code is matched, it will say that there is no error. The idea of such a circuit is that if there is a fault and the circuit is affected by a fault, it will go to a non-code word. Like for example, if I assume that is an odd parity circuit. So this is an odd parity circuit. So always the output will be odd parity. If there is a fault in the circuit, it will just become a even parity. But it can never happen that under fault there will be another code word can come. For example, I say that for input 1, this is the output. For input 2, under normal condition this should be output. But by a fault, input 2 cannot lead to this one. If by input 2 and failure, if you go to this pattern as the output, then your circuit will say is normal, checker will say is normal, this is an odd parity. But that will never happen in a self-checking design, and the faults considered. Rather what will happen, if there is a fault, I2 can be mapped to something like this, which is a non-code word. So that is the basic idea of self-checking circuit using code words. That is, if there is a failure, the output will be a non-code word. But under no circumstances, the output will be mapped to a wrong code word. So that is how you can easily detect the faults. But of course, again some invariant properties, that is the invariant property, that this should happen. And if there is a fault, it should be a non-code word. If there is no fault, always should be a code word which is correct. But there cannot be a wrong mapping to a code word. With a fault, you cannot map one odd parity code to another odd parity code. It will not happen. It will go to a even parity code. To get all this, basically the circuit will have some kind of a invariant property. Sometimes again the circuit has to be modified, and some stuffs are there, as we will see. So, but the we are not going to as much depth of the theory, but finite state machine modeling requires very huge amount of circuit changing to obtain the signature invariant property. But in case of self-checking code based output theory, this change is very minimal, as we will see. So therefore, this is a more popular architecture which is applied for online testing. Examples will make you things very clear. So I take a simple half adder circuit. So we know that this table is basically for your half adder circuit, I think, which you all know. This is your half adder circuit. So 0 0, sum carry 0 0, 0 1, sum will be 1, carry will be 0, and for 1 1 the sum is 0, carry is 1. Very simple. Now we know that in this case of a circuit, any of these inputs can come, any of these inputs may come, and we have no control on the inputs, but still we have to detect whether there is a fault or not. So basically what I will do, they have said that I will use a parity code. So what the parity is, they have taken even parity. Now the property of this circuit has to be made such that if there is a fault, the circuit will be odd parity, and if there is normal, there will be even parity. So I will add an even parity, so 0 0 0, all other cases will be 1. right. So this is this function for sum, this is the function for carry, and this is the function for parity, that is x or y. Now this is your circuit. Let me zoom it for you. So if you look at it, this is your circuit. Now very interesting, this is your cut, this is the device under test, inputs are there, and basically if you look at it, this is your parity generating circuit, this is your parity circuit. And we have already seen the parity circuit here is nothing but x or y. So I put an x or y gate, and this is your parity output, correct? And this is a checker. The checker job is nothing but it just checks even parity, that's it. So now you can see, of course, the size of the cut is much larger than the circuit of a parity generator, and you can assume that if the circuit is quite large, your cut will be much larger. Cut in the sense is circuit under test, which is your basic circuit functionality, which is doing your main function of the circuit, and the parity generator, which is the DFT circuit, will be much smaller than this. So we assume that the failure probability here or the failure probability here is much lower than the circuit which is large in nature, because statistically it is found larger a circuit is, more number of gates, larger silicon area, so the fault probabilities are higher. So if you apply the pattern 0 0, so you will find out that basically sum and carry are 0, and the last pattern parity is again also a 0. So it will find out that the parity is all zeros, even parity no error. Now again let me just take a stacked fault in this line. So if the stacked fault in this line, so basically here x and y will go, so this is the fault over here inside the cut. And one more assumption I should tell you, we are not going the exact proof, but here again we are assuming a single stacked fault principle. Either the fault will be in the cut, or the fault in the circuit, or the fault in the checker. And it has been shown mathematically that this checker based scheme, if there is a fault in any of the either 3 circuits, these faults can be detected by the scheme. Not only the fault can happen in the cut, it can also be there in the parity generator, also in the checker. So anywhere such a single stacked fault is there, this cycle will give you an error. But I am not going into the theory of this, because it involves lot of coding theory principles. Means whenever we talk about VLSI testing, the areas after BIST or starting from BIST is entirely involved in very complex coding theory. So why it happens, what is the proofs of all these are very involved, and we have separate courses of coding theory on that. So for this course, I would request you just to take the words from me and just assume that this is the case, because most of the test engineers rely on this theory, and if very interested ones can go for the proofs. But we all know that this property will hold, so we can apply in the test. So for the time being, the fault can be anywhere, only one fault at a time. So basically the same property will hold. So in our case, we are assuming a fault in the cut, because this is main part of the consideration. So if you look at it, your output will be basically 1 0 1, because this is XOR. So 0 XOR 1 is basically 1. So now this will be 1 0 0, and basically what happens, so the output is 1 0 1, means 1 0 0, so it's an odd parity, so the fault is going to be detected, right? So this is a very simple way of handling parity. So in parity what happens, this parity checker is augmented with the circuit, so that with this expected working output, basically it will add a bit here, so that always in the normal circumstances of the cut parity generator circuit, the output will be a even parity. Any stacked faults basically anywhere, either in the cut or parity generator, will lead to a so-called odd parity that will be detected. Now, so it seems that parity is a very good way of handling it. Just add 1 bit parity and your job is basically done. So even without applying any input patterns, if I observe any problem in the output, your job is done. But before going to this, we all know that parity based coding technique has some kind of issues. What they are? Say for example, there is a circuit something like this. There are a lot of circuits over here, and I have a parity stacked fault over here, and I am using a parity bit encoding, and maybe this is a gate which is a fault over here. So it is output of 2 circuit cones. Cone means the circuit it represents, there is a gate whose the output, primary output of this part of the circuit depends on this, another primary output also depends on the same gate. So let us say that due to this fault, it changes the output from 1 to 0, right? And the same time, as this gate is also controls another output, primary output of the circuit, so also it changes the values from 1 to 0. And we are assuming that there is one more line which is always giving the 1, whose answer is basically correct. So you should have got the answer as 1 1 and 1, right? But due to the modification, it will be 1 0 0, and we are assuming that we are having a, or as in the case we are using a even parity. So here also we are using even parity, so also we are having a even parity over here. So even parity means it will be generating a 1 over here, and also it will be generating a 1 over here. This is the error case and this is the normal case. So this is your expected output. So expected output is all ones are there. So this will be the parity bit will be 1 to make it as a 1. Again, due to this error, what happens? Basically, this 1 is anyway generated, and this one is again this one should be 1 1 1, but actually the output you are getting is 1 0 0. But still again it's an odd parity, even parity, sorry, the even parity, 1 1 1, so even parity, so I have to add a 1. Here also 1 is added because the output was expected to be 1 1 and 1. But due to fault there are 2 bit flips. So 2 bit flips from 1 to 0 and 1 to 0. So even that is what, and again you are not able to detect this. Why? Because parity is a single bit error detecting code. I think it's a very well known theory. So what happens if there are 2 bit flips? So 1 bit flip, which is in the case, you can very easily detect because it is changing from even parity to odd parity. But here are 2 bit flips in this hypothetical example, 1 to 0 and 1 to 0. So if there are 2 bit flips, basically you cannot do anything because the parity is maintained. So if there are 3 bit flips, you can easily detect. 2 bit flips you cannot detect because still the even parity will be maintained. 4 bit flips you cannot do that. So we all know that parity is basically a single bit or even or odd number of errors which it can detect. So but it can always happen that there can be a gate who is controlling 2 outputs of the circuit, and basically it is affecting both of them. So in that case parity error detecting codes will be a huge aliasing code. In fact that is true. Parity technique has lot of aliasing properties. So in many of the fault coverage will be very less, even less than 50% or even lower, because wherever there is a fault which is having multiple gates and there is, and we is also sometimes called it unidirectional error, that is from 1 to 0 and 1 to 0, same direction the error happens. So the parity is balanced and you cannot be able to detect it. So although people first tried with parity way of detecting circuit faults online, but then they find out a lot of aliasing property as expected, and then they started moving to more advanced kind of error detecting codes. So we'll see that this, as I told you, the literature is huge, but today we'll see another one which is slightly better than the parity technique. Before that, we'll just give you a small definition. So basically one definition is called multi-bit error. So what is actually a multi-bit error means there is a change from 0 to 1 or 1 to 0, and it should happen in more than 2 or more number of bits, very obvious. And there is something called unidirectional error. Unidirectional error means basically either the error will be from, in all the bits will be from 0 to 1 or 1 to 0. But there cannot be 2 lines where 1 is the error here and 1 is the error here. So we will see later today that multidirectional errors are very difficult to be detected. Unidirectional error means both way 0 to 1 or 1 to 0, but there are multiple bits can have it. But again you have seen in parity that in parity if there are 2 such unidirectional errors also it cannot be detected. Unidirectional means all 0 to 1 or 1 to 0. Same direction the error changes, and I should tell you that why it basically such type of failure slightly less, because as means people have predicted that unidirectional errors are more possible in circuits. They are statistical finding. So bidirectional errors or multidirectional errors means some of the bits will go from 0 to 1, some will go from 1 to 0. It's an extremely difficult way of, such type of faults are very difficult to detect, and you require a very sophisticated coding theory to do it. And more sophisticated test codes you are going to use, more sophisticated will be your code generator circuit will be and your checker circuit will be. I can do that. I can use a very advanced codes, and I can find out that it will detect multidirectional errors, multi-bit errors, but again this size will be larger and your exercise will be futile. So basically, today we are going to look at a simplified case, in which case we are saying that it is basically nothing but a multi-bit error is possible, but again as you have again repeating, multi-bit error is not possible to be detected in parity. 2 bits not possible, 4 bits not possible, even if it's a unidirectional error. And multidirectional errors, of course, if 1 bit goes from 0 to 1 and 1 bit goes from 1 to 0, so parity cannot do anything because the number of ones are balanced, correct? So because there will be no parity change. But so anyway, so we have already discussed the disadvantages of parity. Parity is mainly basically for odd number of bit changes, that also unidirectional. Right. So now we will be focusing on slightly making the problem bit tougher, where there are bit flips, but the bit flips are unidirectional, all from 0 to 1 or 1 to 0, but it can be in the more number of bits. So multi-bit unidirectional error is what we are going to consider, and for that the parity bits of course will not hold, because already we have given the example, because if 2 bit flips are there, then it will actually change the it will still maintain the odd parity or even parity, correct? So now basically we will see that there is another type of codes which can handle multiple bit but unidirectional codes. They are actually we call unordered codes or unidirectional to detect unidirectional errors. The codes are called unordered codes, and some example of unordered codes are m out of n code. So m out of n code means if these number of bits are say 1, 2, 3, 4, 5. So out of that we can say 4 out of 5 code. So 4 out of 5 code means basically only 4 will be 1. So this is 1 n out of n code. So 1, 1, 0, 1 and so forth, and finally you will have 1, 1. So any of the 4 bits will be 1 among the 5 codes. So this is actually called 4 out of 5 code. That means if the circuit does not have a fault, the output will always be following this code of 4 out of 5. And if there is an error, it will be having some other different codes which will not be 4 out of 5. And that is called Berger codes. In Berger code basically is the binary representation of the number of zeros in the information part or the main output of the circuit. So in this case number of input ones are 1, 2 and 3. So the Berger code will be 1, 2, 3. Okay, so the output should be 0, 1, 1, not 4. So as many number of ones in the output, in this case is number of zeros. So anyway, you can take either zeros or ones. So number of zeros are 1, 2, 3, 4. So the value of C is 4. Or you can also take the number of zeros also. So this will be the information part, and instead of the parity part or some other part, that is the code part, you have to put the binary count. This is also a unordered code. We will tell you what is the meaning of exact meaning of unordered codes right now. But for the time being, you have to just learn the fact, or till now we have carried out the fact that for parity bit the problem is it cannot have multiple bit errors may not be detected, and of course multidirectional faults cannot be detected at all. And also we will see later that multidirectional faults are very difficult to be detected. But still, can we try to do something about multi-bit unidirectional errors? So in that case, we are trying to focus on a new type of coding theory which is called unordered codes. We will see the definition, but before going to the definition of an unordered codes, basically we are basically telling you about two coding styles. One is Berger and one is m out of n code. So I think you just remember this, and we will go to the next slide. So what is unordered codes? Unordered codes are nothing but there are two codes which one cannot cover the other. So what do you mean by code covering? Say for example, I have the numbers like this one 1, 1, 0, 1, and the other number is basically 1, 0, 0, 1. So in this case you can see here 1, 1, here 1, 1, and basically this is a 0 and this is a 1 over here. That means this guy which is x has 1 in all the positions in which the value or the vector y has a 1. So x has a 1 here, x has a 1 over here, here 1 is extra and it's a 0 over here. So you can say that x will cover y. But of course means the idea is that x covers y means that x has a y 1 in each bit position where y is a 1. So x will cover y. But unidirectional codes are something which nobody covers the other. For example, if you see x is 1, 1, 0, 0, 0 and y is say 1, 0, 0, 0, 1. So in this case you see this is x and this is y. So this guy has a 1 over here and it's a 0 over here. These are matched and this is having a 1 over here. So you can see here y is having an extra 1, here x is having an extra 1. So x and y cannot cover each other. So we will say that x and y in this case are unordered codes. Now what is the beauty of unordered codes? You can very easily appreciate the fact over here that multiple single direction bit flips can be detected by this code. So again I want to re-emphasize that in coding principle based online testing, the output of the circuit will always be one code word. So if I take these two as the code words, say, which are covered. So 1, 1, 0, 0, 1 and 1 is 1, 0, 0, 0, 1. So of course as you have seen this guy is actually covering this. So now what happened? Due to some kind of error, again I am telling unidirectional error. So what can happen? So unidirectional is the multiple bit flips. So but single direction. So let us assume that this guy is changing to 1 and again we are saying that multiple bit flips 0 to 1 and so again we can say that this guy is changing to 1. Okay, let me just again take the 1. So 1, 1, 0, 0, 1 and this one is 1, 0, 0, 0, 1, right. So x is basically covering y. And now let us see that what is the case. So we will see that basically if there are multiple bit flips, then what will be the issue. We will show basically that unordered codes can withstand the effect of multiple bits unidirectional error. That is what we are going to see in elaboration. But if there is a, as I told you, if so this one will not be able to tolerate unidirectional bit flips. multiple bit flips. But if the codes are something like this, in which nobody covers each other, it will be easily able to register the multiple, even the multiple number of bit flips, unidirectional bit flip. That is what we are going to show with examples. So I think till now we have I mean, if you are with me, so we are looking at some kind of advanced codes compared to parity, which can withstand multiple bit flips but unidirectional, and for that we are going to use unordered codes. And of course, as you have seen that this is actually an unordered code, you can easily appreciate. Now of course, you have to appreciate that this m out of n code, I am taking an example of 4 out of 5 codes, you will be appreciating that this is a unidirectional code. Why? Because, sorry, it is an unordered code. Why? Because you see all the lines, all the bits, all the vectors will have at least 4 ones. So you can see that this one is having a 1, this is having a 0, here this is having a 1 and this is having a 0. So what it means? It means that basically none of them can actually cover each other. Similarly, if you look at it, the last 2 bits, so this 2 is having a this one. So the last 2 bits basically, if you look at, so this one is having a 0 and this is having a 1 and this is having a 0 and this is having a 1. So none of the vectors can cover each other. So hot 1 encoding, hot 1 means only 1 bit is a 1, m out of n code, I have given the example with 4.5, none of the code words can cover each other. So basically what we have said, we have basically what we are discussing over here is something like, so that means the m out of n code basically is a unordered code, because none of the bits are covering each another. That we have explained using 4 out of 5 coding technique, that is m out of n. And by this definition, we have looked at that this is a Berger, m out of n code is a unidirectional, is a unordered code. Now what remains, we will try to develop the philosophy that such unordered codes can detect unidirectional multiple bit errors. So indirectly we will show that if you are having if you have say unordered codes like m out of n code, Berger's codes, and applied to circuits, so if it happens that a fault will lead to multiple bit unidirectional errors, this can be detected. So it will be a much better efficient compared to a parity code. Why? Because the parity codes can only withstand mainly single bit flips, and if there are even number of bit flips are there, even if they are unidirectional, it will not be able to do it because the parity count is maintained. Okay, same example we are going to do, and we are going to get the philosophy. So in this case, same half adder you are using, but instead of basically using the parity bit, here we are using a 2 out of 4 code. So only 2 bits will be a 1. So 0 0 means the option is nothing but you have only the option of having 1 1. 1 0, so you are using the option of 1 0 over here. 1 0 again you are using this one. These two you have to be a bit careful because the two numbers are same as the output 1 0 and 1 0, but you are using the code of 1 0 over here and 0 1 over here as the code. But again if you count, there are only 2 ones in each position. Again it is a 0 1, they have put the value of 1 0 over here. So basically this is basically your information part and this is your code part. Now you see, so in case of parity, the extra bit was 1, here the extra bit is 2. So I keep on always telling that hardware cannot create any magic. Hardware is always better performance you want, you have to pay a cost. So parity you can detect only single bit errors. Here you are detecting multiple bit errors, single unidirectional errors. So you are using some kind of a code techniques which are unordered codes. Still see the number of bits have increased. Output bits for the parity was 1, now it is basically 2. Of course some benefit you are going to get, but again of course the cost etc. will be higher. So again this is the function for sum, this is the function for carry, and the 2 bits in this case, so this is the function for u1 and this is the function for u2. Now you look at it. So if you look at the parity circuit, there was just a single gate required for this. Now for this one you see you require a quite larger circuit to check bit generation. In this case basically it is check bits. Right. So more facilities I want, I will require a larger circuit. So here you may argue that this check bit generator circuit is much larger than the card. In fact, this is a small example, so it looks like that. But if in case of real practical circuits, the technique of error detection codes of Berger or m out of n codes are much lower than the circuit itself. So if you take large circuits, this automatically happens after synthesis of the circuit. So I apply 0 0. So you can see I have applied 0 0 over here. So basically the output is normal case will be 0 0 and the parity bit generated will be self-checking code generated will be 1 1. So in this case the output will be 1 1, as you will see over here, it will be generated by the circuit. So it is 0 0 1 1. So the checker finds that there are 2 1s out of it, so it is detected. Now I again apply a stacked fault in this case. So I apply a stacked fault. If you apply a stacked fault, you will find out that this parity generator circuit will always put 1 1 as the output, because the expected output was 0 0, but because of the faults this bit has basically changed. So this bit has changed, and in this case you are going to see that the 3 1s are coming as the output, which is violating 2 out of 4 codes, and the checker will basically detect an error. So this is the, so in this example you cannot exactly find out what is the benefit, because you are both detecting using stacked using parity, as well as you are detecting using m out of n codes or 2 out of 4 codes. Then you can ask me what is the benefit. Just as a homework you can try doing it. You take a, as I told you, you take a circuit where is a gate, correct, and basically there are 2 flips out of it. So the fault over here is basically making a flip of 1 to 0 over here and 1 to 0 over here, and assuming that there was a third output, as I told you, which is a 1, and you take even parity. So in this case the parity will be generating as a 1, and in this case also this one is a 1, and in this case also parity is a 1, but as there are 2 bit flips, parity will not be able to detect. Now you go for a m out of n code. You do m out of n code. So basically in this case it will not be a parity. So in this code this is let us take a m out of code, assuming that it's a basically 3 out of 4 code, that you can assume. So 1 2 3. So 3 out of 4 code means basically, or you can take 3 out of 5 code. So this is the first output, second output, third output. So all are 1, and this is the code words are all 0 0, because we are assuming that basically it's a 3 out of 4 code. Now basically in the normal mode the output is going to be a 1, as simple as that, and basically as expected it will give the value of 0 0. Now you see the error will be easily caught. Why? Because the number of 1s is 1 0 0 0 0, so only 1 as the output. So parity will not be able to detect it, but the m out of n code, in this case the m out of n code is 3 out of 5, it will be able to detect it. Why? Because normal case the answers will be, number of 1s will be 3, and the fault case the answer will be actually 0. Again, I mean, just again appreciating the fact, even if this bit also becomes a 1, sorry, even if this is the 4th bit we are considering. So if you are taking the 5th bit, first bit basically, or the 4 output, even this also gets flipped from 1 to 0, that can also be detected, because 1 2 3 all zeros, basically output should be basically 3 1s out of 5. Again this is very important, so again I am just repeating for the sake of understanding in a very different manner. So in this circuit, as I told you, the difference is not actually being captured. The idea is why, because in this case even if it is stuck at 1, this is feeding to the AND gate, so the effect of the fault is not observed. Like in this case also, this is a stuck at 1, and if you look at it, this wire is also going to the AND gate. So AND gate stuck at 1 does not get into a picture for this input case, right? But as I told you, what you can try out, basically something like you take some other input, maybe this same circuit or some other circuit, you try to take a picture where there is a single gate, but it will affect 2 outputs at a time. Also you should have a third normalizing output. In this case it is only 2 outputs are there, both will be affected, but in your example you can take another output which is not be affected, and assuming that the output should be, normal case should be 1 1 1, and parity I have already told you, and you are using a 3 out of 5 code, so you will put a 0 0 as the code. Fault, as I told you, it may have the flip from 1 to 0, it can have the flip from 1 to 0. So, and this is your normal one, normal bit which is not changed at all. So as the bit added, but the coding will be 0 0, because the expected answer is 1 1 1. So here we will be easily detecting the error, because the number of 1 counts changes. Similarly, we can also appreciate the fact that basically for parity it cannot be called. Same thing also can be tried out in the example, but you just check for a different test pattern. So now one idea is that, saying that you can ask me that I am telling you that for the same circuit for different input pattern the fault will be aliased. Then I should worry or I should not worry. In this case I should say I should not worry, because in this case I require at least some of the test patterns should detect it. It may not be always possible that for all patterns the fault will be immediately detected. If you want to do that, the cost will be exorbitantly high. High means what? For, as I told you, for this circuit, for this scheme, or even for the, let me take the, not the good scheme basically, that is the parity scheme. If I see, I can tell you that for this input pattern, for this fault, this even by the single parity bit it is detected. But you can easily find out that in this circuit it may happen that for some other patterns basically the fault will not be detected by the parity scheme. Then you should ask me whether I should worry. Basically it's a matter of fact that you should worry or not, it depends on the certain circumstances, because I know that for at least this pattern 0 0 the fault will be detected by the parity scheme, but it may not be detectable for some other pattern, say 1 1, it may happen. then basically what should I do? Of course, by the pattern 1 1 it will not be detected because it's stuck at 1 over here and the fault will not be activated. But should I worry? Because here you have to understand that here I do not have any scope to apply the pattern of 0 0. So if the pattern 1 1 comes, the faults will obviously not be detected by any scheme, even forget about parity, because the fault is not sensitized at all. But again, I have no scope of directly applying the pattern 0 0. I have to wait till the pattern 0 0 comes. So I should not be very worried about it, because I am expecting that sometime 0 0 will come and the fault will be detected. Only my main concern should be if there is no pattern which can detect a fault. That means there is, for any of the patterns which could have detected the fault gets aliased because of this the error detecting scheme. Then I should be very worried. Again, repeating, this is a very important concept, so I am repeating it again, that given a circuit, maybe for some of the input patterns and the coding scheme selected, the fault is aliased or the fault is not sensitized at all. I don't worry at all, or I should not worry that much, because as long as there exist some patterns for which the fault will be sensitized and it will be detected by the parity or by the coding technique, then I should not worry that much, because I expect that the pattern will come. But if it happens, because I always think that all patterns basically come at regular interval, but if you have made a mistake or there is a problem, in which case what happens? Basically, if you try to think in this direction, that you are landed into a situation where for the circuit none of the patterns will be able to detect the fault because of aliasing properties of the circuit fault, or fault getting masked, or some other reason, as you have shown the parity code or some other code may not be able to detect the fault, and for any of the pattern the property holds. There is a question of big worry. So we should always try to think in that manner, that there should be some patterns for which the fault will be sensitized and detected by the coding technique. Then I am happy with it. But on the other hand, we should be very worried if no patterns can do that for the coding technique used. That is what is the idea. So therefore, in a nutshell, we have seen that basically we will take a circuit, have some coding technique applied, and ensure that at least for some of the patterns the code will be detected. Then I will be very happy. So this is one way of handling the online testing methodology. But again, so in the conclusion, what they have said, that single stacked faults in the circuit can be detected if such a fault result in either a single bit error or unidirectional multiple bit errors at the outputs, and the outputs are encoded using single or unidirectional error detecting code. That means it has been shown theoretically, if the circuit has been encoded using single error detecting code, that is parity, or unidirectional multi-bit code like m out of n code or unordered codes, then stacked faults will be detected if they lead to a single bit output fault or multiple bit unidirectional fault. But again, if I change the statement, that if a fault results in multiple bit non-unidirectional fault, that is, one will be going from 1 to 0, another will be going from 0 to 1. Such situations also happen, but that is very difficult to get detected by simple error detecting codes. Very complex techniques exist, but that will make the circuit tester monitor very large. How will you handle such kind of non-unidirectional errors? That we will try to focus in the next lecture. Thank you.